Good morning. Let's recap what we did yesterday. We started looking at several devices through which we do thermodynamic processes, and those devices were selected because that's what we have in real life. That if we need to make a machine, we would make combinations of those and put it together. So theory tells us that there are a lot of things possible. In practice, there are some things possible, and on that also, there are certain restrictions in their use. So we will continue with that, and then we will look at how we can use all of that knowledge of what is possible, what is theoretically possible, but what is practically realizable. And then we'll look at how we can, what the closest one can come to creating a Carnot cycle. After that, we would have also gained experience in saying that if these are the devices on which I want to make a solution or a problem is given, what is the way in which we go about solving it? And so the first part of it is what we have now done. Tomorrow I'll take up examples where we'll start actually putting some numbers and see a variety of problems over there. So this is what we have been looking at: realization of thermodynamic processes. What are the types of devices that we have? These are theoretically possible, and practically, from the world of engineering, there are limitations. And what we have done is, even with those limitations, we have seen what are the implications of those limitations on the thermodynamic performance of these devices. So yesterday, we looked at these devices, positive displacement devices. In particular, something that keeps coming up, and we'll look at it again, is the cylinder piston arrangement, a closed system in which working substance does various things. Then we looked at the idea of what is the heat exchanger, and we learned that a major assumption we make in heat exchangers is that heat transfer processes, when they are flowing through a tube, the fluid, they are assumed to be constant pressure processes. So that is possible. Then we looked at compressors, where we take an ideal gas and increase its pressure relatively in large amounts, and fans and blowers, where the pressure rise is relatively small and flow rates are high. And both these, we said, are work input devices, and in the ideal case we said that this would be at best isentropic. And we also saw that the way we get these machines, we do not add heat into these devices. In reality, if it is running above a temperature, there will be a little bit of heat loss from the surface to the ambient air. Then we looked at pumps. We said these are devices that take a liquid and pump it to a higher pressure on a continuous basis. So here is also work input is there, and we said that the ideal case was isentropic, like the compressors, fans and blowers, and what would be the real case where this entropy increases. And we looked at the last machine yesterday was the turbine, and we looked at gas turbine, we looked at steam turbine, hydro turbines, and we said these are work producing devices, and the most efficient way that we can get them, thermodynamics tells us that there should be an isentropic process in these turbines. And we said that if this were real machines, then there is some irreversibility in the flow, then operating between the same pressures, what does the process look like? So these were the things we looked at. So today, now we will look at another list of things. We will continue some of this I had put up yesterday. We will now look at a nozzle, then we look at a diffuser, then expansion valve, or something in which throttling takes place, a pipe, tube or a duct flow, just a plain flow. Then we look at mixing of the same substance, not mixtures of two different substances. Then we will look at separation, particularly in a wet region. And finally, we will look at unsteady processes like filling or evacuation and emptying of a tank or a reservoir. So let's start with the nozzle. So this is a device which accelerates a fluid. In the process, the pressure drops. And a typical sketch of this would look like this, in which the working substance enters here and exits over there, and we make this as a system, saying that the system boundary is everything that is inside this nozzle, and to that we apply various laws. So once we made the system boundary, we see that there is something moving in here, something moving out. So our first step in the analysis is to decide whether it is what is the system boundary. We did that. Whether an open system or a closed system. This is an open system, and then we say, well, now I have to apply equations which are the control volume equations. We have one inflow and there one outflow, and that tells us that this is state 1. We call this state 2. That m dot 1 is equal to m dot 2, and then we say, well, what does the energy equation tell us? It tells us that in this case we make the important assumptions there, that first it's a relatively small device and we try to insulate it if possible. So this is adiabatic. There is no heat transfer during this process. Then we also say that there is no work transfer happening across this, so there is no work. And so there are the things that happen, but the size of this is relatively small, so that means that we can safely assume that delta change in potential energy is 0. And the very first assumption, like we did yesterday in all the analysis, steady state. That means nothing changes with time. So we said delta PE is 0. But because this is a device that accelerates a fluid, there is no way we can assume that kinetic energy changes are small. So in this case, what is clear is that V2, the velocity, is greater than the inlet velocity, which is V1. If one of these values is given, say V1 is given, then we don't need to make this assumption. But the important thing then becomes that if we solve the energy equation and simplify it, then we get H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. This is what we get. If V1 is given and the conditions states 1 and state 2 are known, then H1 and H2 are known, we can calculate V2. So that's the analysis of a nozzle. And this doesn't matter whether it is an ideal gas or vapor. The processes are the same, and we have to show it on a TS diagram. If we are looking at something which is in the wet state like that, then a nozzle ideally would be without any irreversibilities. So this would be S equal to constant, or an isentropic process inside this. So if the initial state is there, we can say that ideal case it comes down to this pressure. So this was P1, this is P2, and this is what the nozzle would do. A real nozzle, this is isentropic part, a real nozzle would have irreversibilities and it would come to this point. We could have put a nozzle there also and accelerated the fluid there. Or if you are far away from this dome in the ideal gas region, say somewhere here, then also it is the same thing. This is 1, this is 2, and the gas is accelerated. If there are irreversibilities, the gas will then reach this point. This dome will not appear, but this is the process. So the process actually looks the same as that of a turbine, but the difference is that in the case of a turbine, there is work output. In this case, W dot CV, the work output or input in this is 0. And the drop in enthalpy goes to increase the velocity at the outlet. So such devices are used in turbines, compressors, and many other applications where you want to accelerate the fluid and get some benefit out of that. So that's a nozzle. And the opposite of the nozzle is what is called a diffuser. So here we look at what is a diffuser now. So this is a thing which decelerates the fluids. That means in the direction of flow, the velocity goes down and pressure goes up. So what's happening here is that we have a flow coming in and then the area opening up, and the flow goes out over there. So we say that the diffusing part is the one where the area is large. So we say this is our diffuser, the control volume. So this is the system boundary, you can say. And there is one inflow taking place here. So this is state 1, inflow into the system, outflow is there, state 2. So with that, we put this thing together and say that first, this is an open system. So we have to apply the control volume approach, and we use the flow equations that we have developed. This is 1, this is 2, entry and exit. Again, like the nozzle, here also we assume something. First, steady state. The second assumption is that there is no heat transfer, so this is adiabatic. Q dot CV equal to 0. There is no work. W dot CV equal to 0. And changes in potential energy, these are very small, they are big. But because the primary job is to decelerate a fluid, it means that velocity changes are substantial. That is the main purpose of this device. So kinetic energy change being 0 is not an assumption for the diffuser. So there is one inflow, one outflow, and the energy equation becomes exactly the same what was there earlier for the nozzle. This is V2 square by 2. And so in the direction of flow, the enthalpy will change and you have decrease in the velocity. So if you plot it on a TS diagram, if it is an ideal gas, there will be a state there. It is ideal case if we assume this is that S is constant, isentropic. So it starts from here and it will go, say, there. State 1, state 2. If it is a real case, then this is the isobar. This is the isobar here. Entropy has to increase, so this will go over there. And you can check from the TS diagram that what it means is that this, it has been taken to the same pressure, but now the temperature has gone up. So this was 2 isentropic, this is the 2 real case. The process looks very similar to that of a compressor. But the difference is that here work transfer is 0. The only change that the enthalpy difference does is because of the velocity change. That's the difference. And if you were near the dome, the same thing would happen, that if your initial state is over there, then we would like to bring it up there and increase the pressure. So that's what diffusers do. And you use diffusers in places where you have very high velocity, which you want to reduce. And one of the places where such a device is used is the exhaust of a turbine, where as the gas goes through and expands, its velocity also increases, but we cannot increase the area so much that the velocity can be kept low. So what happens is the exit velocities are high, and then we do not, if we want that kinetic energy to be recovered for some purpose, we can then put a diffuser there, recover some of that energy, and then throw the gas out. You will also see this in rockets, where at the bottom you will see a device looking like this, where you got high velocity fluid coming in, low velocity fluid goes out. In the process, the pressure increases, and this is what generates the thrust on rockets. So this is a very important part in the design of propulsion systems. The way we achieve nozzles and diffusers, although I have drawn it here as a pipe, in turbo machines, we achieve this as making a passage between 2 consecutive blades. So if you look at 2 blades and we draw the shape there like this, so this is, say, 1 blade and this is a second blade. Then the purpose of this is that as the gas or the steam flows through this, we take this as a system here. And what I've drawn is a blade of this cross section which is normal to the plane of the paper, and there are many such things on a shaft. So they make a circular thing which looks like a turbo machine rotor or a nozzle. But the thing is that when this enters here, it sees this much area. Normal to the paper, the height is the same. So this is the inlet plane. At the outlet, this has decreased. So these two things together produce a flow passage where the area decreases. And this would mean that this would act like a nozzle that will accelerate the fluid. So between this inlet state 1 and the exit state 2, H2 will be less than H1 and the velocity at 2 will be greater than velocity at 1. So that's what one does in turbines where we have high pressures, say steam or gas, we accelerate it and then we pass it over a rotating set of blades which imparts momentum to it, and that's what causes the power output from a turbine. The opposite is done when we look at compressors. So you have the same shape, but now you are putting in from this side and you decelerate the fluid. So this is a realization on turbo machines. The idea is that we create passages. It does not necessarily have to be concentric, it doesn't have to be straight, it could be of any shape, and we can get this type of performance from the device. The next thing we are going to look at is a device which we call, something we will call a throttling valve, but some places also known as an expansion valve, and popularly we also see these as pressure regulators. So all of them in construction would be slightly different, but in all these cases what we have done is that we just have a small constriction in the flow, and this flow could be passage through a valve, which means that there is a body into which it enters from one side and we have a small constriction there. As the fluid goes through this, there is a big pressure drop, and that's all happens over at the outlet. This is a small device, so what one does is that we assume that this is a steady state system. The control volume would be like this, or in this case it could be like that, and here we have something coming in, going out. This is state 1, this is state 2. So this is an open system, and we have to apply the control volume approach. We assume that it is steady state, there is no heat transfer, adiabatic, there is no work transfer, it is just a simple stationary device, nothing moving. Then we also say that here velocity at the inlet and outlet are comparable. They are not very drastically different. So it's not like a nozzle in any sense. And of course it's a very small device in most cases, and we can say that changes in potential energy are zero. So the conservation of mass equation tells us that m dot 1 is equal to m dot 2, and the conservation of energy tells us that H1 is equal to H2. And so this type of a process is isenthalpic. Inlet outlet enthalpies are the same, but what we have done is we had a high pressure, high temperature here, we got a much lower pressure on the outside. We would know from the second law analysis that S2 is greater than S1. Throttling is a hugely irreversible process. Which would also mean that you would like to avoid it as much as possible, but then there are certain practical aspects of the throttling process which are very, very nice. And where do we see throttling taking place? Firstly, we can see that in all your refrigeration cycles, where what we have done is that is the pH diagram, and on this we can plot the dome, and after subcooling the liquid from the condenser, we have to bring it down to this pressure. One option is that, okay, let's put a small turbine, generate some work and come to this state. Entirely possible. Thermodynamically, it is nothing can be, it's entirely feasible. Practically, for the size of the machines that we have, refrigerators and air conditioners and even large devices like central air conditioning plants, the work output of this will be so small, the machine is complicated, and second, somewhere it is handling a liquid, somewhere it's handling liquid plus vapor. That makes the machine very practically impossible to make in the engineering world. So we do not have work transfers taking place like this. And as we saw with turbines, in general and pumps, we do not want any work producing device that operates like this or operates like this or there or there. We want work producing devices to either handle only a vapor or a gas or only handle a liquid, not mixtures of these two. Such machines cannot be made. Okay, so in the refrigerator, we cannot put a turbine. The second option we just learned, why not put a nozzle? We can accelerate it, it's an isentropic process, but the trouble is that by the time you drop the pressure, the velocities are so high, it becomes difficult to manage the machine. So the next easiest thing one does is to just throttle it. And throttling is an irreversible process. We don't know exactly what happens in the intermediate states, but it brings us from there to there. And that can be done either through a wall, or we put the refrigerant suddenly through a very narrow tube where there's a very large pressure drop. That's all it does. In the process, a subcooled liquid becomes a saturated state and the wet mixture that you get here. So that's what we use throttling for in all refrigeration systems. The second application that you would all have actually seen is your LPG stove. So on the top of the cylinder, you have a small device, something looks like this, and this is sitting attached to the top of the cylinder, and from one side of this, there's a tube going out. That is the pressure regulator. Without that, we cannot use the LPG regulator. What it does is that there's a very small opening over here, which is controlled by an automatic spring device, which senses the pressure over here, it senses the pressure over here, and depending on the difference of the pressures, it adjusts the position of this, so that inside here, which is saturated vapor at say 3 bar, 4 bar, something like that, that is reduced and brought down to a pressure of 600 millimeters of water column. That is a throttling process. So we have just throttled it from say 3 bar or 4 bar, somewhere in there, to 600 millimeters of water column. That's a much lower pressure. So this is a very small opening, like a millimeter in diameter or so, through which this vapor passes. There's a lot of friction that it goes, and its pressure drops, but enthalpy remains the same. There is not much change in velocity. Potential energy changes are very small, and you get constant pressure over here. So that's the device of this, and that's why it is called a regulator. That no matter how much gas you are using, whether you have gas on low flame or on high flame, this will always put out, by adjusting itself, 600 millimeters of water column pressure here. Where it begins to have a problem is that when the cylinder is getting empty and the liquid is all gone, then 3 bar pressure, as you keep drawing the gas, will start decreasing. In which case, after some time, this regulator cannot do its job. This pressure begins to fluctuate, and you see that the stove is now giving an unstable flame, and that's a good indication that the cylinder is about to go empty. So pressure regulators is another very important device, not just here in LPG, but you can see any machine which operates on CNG, as CNG operated bus or auto rickshaw or taxi, the cylinder pressure is 200 bar. You cannot put that into the engine. So there is a pressure regulator, maybe 1 or 2 stage pressure regulator, that bring it down. From here, pressures could be as high as 200 bar and brings it down to again something like this pressure, few 100 millimeters of water column. So these are also used in industry, where you say that I need to have, say, steam coming into a device at 10 bar. But your supply comes anywhere between say 11 and 13 bar. You always give some margin there. And so you do a small amount of throttling so that outlet pressure is always 10 bar to the device that you want. So these are very commonly used. Because of this very precision movement inside this, these are very, very sophisticated devices, and the engineering of this is quite a challenge. But the fact is that these are commercially available. A lot of these are available for many different applications, and they are used very frequently in process industry. Okay, so this is the idea of a throttling valve or a pressure regulator or an expansion valve. It need not even be a valve, as I mentioned. In refrigerator, it could just be a long, very thin tube through which, as the refrigerant goes, because of the frictional pressure drop, it achieves the purpose of throttling. Okay, so that was what happens in a pressure regulator or an expansion valve. And it's a hugely irreversible process. So if I have to show this on a TS diagram, and the saturation dome is say somewhere there, the constant enthalpy lines, they run like this. These are constant enthalpy lines. So the throttling process on the pH diagram, which look like a straight line, say between this pressure and this pressure, it will actually follow a path and come finally to this state. So this would be the throttling on the TS diagram in the case of the refrigerator. But if you are throttling superheated steam, then it could come from there to there, or maybe there to there. So in every case, it goes only in one direction. It's an irreversible process, so the opposite process is not possible. Unlike say, nozzles, unlike diffusers, turbines, pumps, all of those ideally we are shown to be isentropic process, which means that you could exactly do everything in the opposite side and run it in the other mode. Here it is not possible. This is hugely irreversible. And the only other thing that comes out to be interesting is that the constant enthalpy lines further away become constant. And so this region, which is the ideal gas behavior, these lines are constant, which tells you that if you throttle an ideal gas from there to there, this should be a dotted line, it's an irreversible process. Throttling is a constant temperature process, isothermal. And that means that that's only when the velocity changes are very small. Other examples of throttling is like you suddenly let out steam from a pressure cooker, or there's a puncture in a tire. So what you have there is say a vessel or a device which has a very small opening, and through which the fluid is leaking out in this case. We all know from experience that if air leaks out and comes out here at high velocity, it also feels cold. That means compared to this, the temperature has decreased. So this is opposite to what we have just seen over here. And the reason why that happens is that here velocity has increased quite a lot. So there is part of it, some of it is like a throttling process, some of it is like a nozzle. In a nozzle, if you increase the velocity of a gas, which would happen here to there, you could see a drop in temperature, and that's what we see happening over here. So this idea is exploited in gas-based air conditioning systems, where you expand the gas and you produce cooling. And an example where that type of a cooling is used is all aeroplanes. So inside the plane, the air is either heated or cooled. If it is hot outside, on the ground, it is to be cooled. So that's what is done. And when you are up flying at 10,000 meters, the air temperature outside is minus 40 degrees Celsius, in which case the compressed air, which is at a higher temperature, is slightly throttled and put inside the passenger cabin to make it nice and cozy. But those are not entirely throttling process. You are partly using the effect of a nozzle also. Okay, so that was throttling. Now we come to something which is somewhat trivial. You wouldn't really find that being discussed in many books, but this is essential to completing a flow cycle. And what it is flow through a pipe or flow through, like water flowing in a pipe, or steam flowing in a pipe, or oil flowing in a pipe, or through a tube. Tube means basically inside diameter is relatively small. Pipes inside diameters could be very large, all the way down up to meter, 1.5 meters, 2 meters. Tubes are small in diameter, few millimeters, 5 millimeter to 8 millimeters types, and ducts. So duct is the term used into which we have a gas or an air flow. So if you have seen air conditioning buildings and you have big square or round things moving around through which air is going, those are ducts. Now, why do we need these? So yesterday when I started off, I made a picture of a refrigeration system, and I said that there are 4 items there. There is an evaporator, there is a condenser which gets compressed gas from there, and evaporator, expansion valve, this could also be a symbol for it. And the thing is, these devices we have just seen now, what is the thermodynamics of that? To make a system practically, we have to connect them in the right sequence. And this is essential to all flow systems and flow cycles. So what we are showing here to here is a pipe. Here to here there is another pipe. Here to here this is another pipe. Here to here is another pipe. And how do we treat these in the thermodynamic analysis? That is what we are going to be looking at now here. So ideally what we have is we can make a, and we say that, well, if it perfectly, first, what is the system boundary? And the system boundary we say is just this one, all the fluid inside the pipe over a certain length, and it tells us that there is inflow happening here, this is state 1, outflow happening here, this is state 2. And this immediately tells us that first and foremost this is an open system, which means that we have to apply the control volume approach for analyzing this, which tells us that one inflow, one outflow, if we assume, first we assume steady state, we can say that changes in kinetic energy are pretty much zero. The pipe is neither accelerating nor decelerating the fluid, ideally speaking. And in 2 cases, ideal case, we can say this is isentropic. In the real case, when it is irreversible, it is because of friction in the fluid and between the fluid and the walls of the pipe, because of which there is a pressure drop, because of which there is a enthalpy drop. So that's what real pipes do, and we know that there is a pressure drop in that. The theory of this you learn in a course in fluid mechanics. But thermodynamics tells us that under these assumptions, this is what will happen in a pipe, and if we either assume that this is isentropic, there is no work transfer in this, so W dot CV equal to 0. In the ideal case, Q dot CV is also 0, but even if this is 0, internal irreversibility if are there, this could cause a drop in pressure. So what we do in treating pipes in a thermodynamic system is that if that's the thing and we are looking at a TS diagram, what we are saying is that if a flow is taking place, then the state will remain the same. But if it's a real flow, then this was the isobar through which this point was there. There will be a pressure drop, it will come here, pressure drop being an irreversible process, and since there is no heat input output, enthalpy is remaining same, there's sort of a throttling type of a thing happening here, the state here will come down. That's what would happen in a real pipe. On the PS diagram, when we have the dome there, we say that okay, we are pumping it from through the evaporator from here to there. Ideally, we assume it to be a constant pressure process. Practically, the pressure will be slightly less, and so the process will actually be something over there. So practical design of these type of systems, we will take care of pressure drop in every one of these pipes. Most of them are insulated, so we say, well, insulation is there and we can as a first approximation, we can say that adiabatic Q dot Cv is 0. And then the diagram which looked very simple will actually start looking a little more complicated. I'll just make one diagram as an illustration, and this is on the pH diagram. So this is the dome, and the ideal cycle says this is the compressor outlet, this is the compression process, this is inlet, this is outlet, and we assume that the condenser, ideal condenser, would be like this. The real condenser, it will get to a slightly lower pressure than this, and so the process then have to be shown by this line. Throttling, of course, did reduce the pressure, and this process though, if you want to come back to this point, we would then have to go through this. This would have been the ideal case, but because the pressure drop takes place, it will come over there. So that's the sort of a changes that happen to the diagram when we do the analysis of real cycles. We will not go into the full details of that part right now here, but the fact is that while we will do analysis of the ideal cycle there, assuming that there is no pressure drop in the pipes, we should know that if I have to treat the pipe, there is a very simple way by which the thermodynamics tells us what we should treat it as, and we can factor that into the cycle analysis. Ducts are nothing but air flowing through them, and the same theory applies to duct flows. Where this is important for pressure drop and all these pressure drops have to be ultimately taken up by the work input device, which in this case is the compressor. If it is a water system, then all the pressure drop in the pipe has to be taken care of by adequate pressure build-up in the pumps. So your pump design, your compressor design, the fan design, they depend on the design of the pipes and also pressure drops which will take place within the cooling coils or some heating coils or some other tubes. So that's where this is important. Now we look at something quite different, and the first thing here is mixing. And by mixing, we are only saying that we are mixing two phases or two streams or two parts of the same substance. So you can take hot water, cold water and mix it and say, well, what do I want to know? I want to know what is the final temperature, for example. So here we will see that there are some other possibilities also. First, there are two possibilities that we will look at. In one, we take saturated state, saturated liquid, and mix it with saturated vapor. And anything else other than this is what we will look at over here. So what we are saying is that we could have either compressed liquid or saturated liquid or a wet state, and we mix either this and this or superheated state. So we are mixing this with this, or this with this, or this with this. The point is that in this case, when we mix the two and we say that they are at the same pressure, the pressure is constant, then by just putting them together physically, there is no change in temperature or in pressure. We assume that these are adiabatic processes. Q dot Cv equal to 0, W dot Cv is also equal to 0. Changes in potential and kinetic energies are also 0. In this case, this will not be true. It will come to some other state. So let's say for practical example, and then we will see on the property diagram what actually happens and why we are even considering such a situation. The one thing is that if we have, say, superheated steam or any other substance going through this, like say superheated, If we want to control and maintain its pressure, the device to use is a pressure regulator. So it will throttle it. So you can only reduce the pressure and maintain it constant. You cannot increase it. But what if I want to reduce the temperature of this? Then theory will tell you that if you have steam at a certain temperature and pressure and if it is superheated or saturated and you want to reduce the temperature, there is either you expand it in a turbine or you expand it in a nozzle, both of which are not practical in most cases. Then the only option left is that it should lose heat to something else, or we should mix something cold with it. So what one does is, if we have superheated steam here and we want to reduce its temperature by a small amount, what one does is that through another pipe, we put in compressed liquid at a lower temperature. So this is at T1, this is at temperature T2. T2 is very much less than T1. We inject very small amounts of this, it comes out as drops, and after a while it evaporates and mixes it and produces superheated vapor over here, whose temperature T3 is less than T1. There is very little pressure change in this process. To inject this, you would have brought it in at a higher pressure than P1, but then it would immediately get throttled and then this liquid will come out. So what is happening is that if you can control this flow rate here, then you can adjust the temperature over here. So in any process, and especially say in power plant, when you say that the turbine inlet temperature has to be fixed at this value, we cannot just by heating steam produce that temperature. We produce a slightly higher temperature, and then by injecting small amounts of this, we are able to maintain the temperature that we want. So this type of a device is called a de-superheater. And this allows us, in the practical world, temperature control. So there is hardly any power station where it won't have this type of an arrangement before the steam enters the turbine and starts the expansion process. So here what we are doing is, we now have to do the thermodynamic analysis of that. So we make the system boundary here. We exclude all the metal and we say, look, this is only the substance that is coming in. So we have one state here coming in, a second state here coming in, state 2, and a state coming out here. This is state 3. So this is an example where in this control volume, we have 2 inflows and 1 outflow. So the analysis of this will proceed exactly the same way that we have looked at before. We know this is an open system, so we write the conservation of mass as before. But before that, we make all the assumptions that we need to do. We say that first, of course, it is in steady state. Then we say that changes in potential energy are very, very small. The device is very compact. Changes in kinetic energy are also negligible. We do not accelerate the fluid very much here at all. And there is no heat transfer to it. This little whole device is insulated, which means that this is adiabatic. Q dot Cv equal to 0. And there is no work or pumping happening. So W dot Cv equal to 0. So if you do all these assumptions, conservation of mass tells us that m dot 1 plus m dot 2 will be equal to m dot 3. So mass flow rate has increased a little bit, yes. And the conservation of energy, the first plot tells us for a control volume that m dot 1 H1 plus m dot 2 H2 is equal to m dot 3 H3. And so if we know states 1 and state 2 and we know the 2 mass flow rates, then there are 2 unknowns left, outflow mass flow rate and the outlet state. So we can use this equation to get the outlet mass flow, and from this equation we get H3, which is specific enthalpy of the final state, and this process we assume is constant pressure. which means that P3 is equal to T1. And that tells us that state 3, we know P3, and from this equation we calculated H3. These are two independent properties. State 3 is completely defined. We can get temperature also and all the other properties. So this is an example where we are mixing two things. A similar thing is also done in refrigeration systems and air conditioning systems, where if you want to control the temperature of, say this is the compressor, and after condensing we have expanded it, and we want to control this temperature now. There's very little we can do by controlling throttling in this. There's a very small amount of range one can do. The rest we can then do is by taking something from here, putting a flow control valve over there, and injecting small amounts of this into a device at this point, which controls the state over here. So you can control this and adjust the temperature at the outlet over here. So these are practical things where in reality you don't have a system that will always do what the thermodynamics tells you is done at one state. But in real systems you have to operate at lower capacity, you need to shut it down, you need to start it up, and all of that we need to do in a very safe and a secure way. And so many of these devices have to be added on to make the system practical. It makes the system complicated, but that doesn't matter. Ultimately, when you want to analyze it, this is the way in which we can go about and see, well, what is it that I'm doing over here. Okay, another example of mixing I'll give, and this is a very common thing which is used in all steam systems, which is called a deaerator. This is exactly the opposite of what you get in aerated drinks. In an aerated drink, we take water and compress and put carbon dioxide into it, and that's what you get your soda pop. In a deaerator, our objective is exactly the opposite, that water and water that we drink or comes out of the tap or whatever we have has dissolved air in it. Dissolved air means O2 and N2 are dissolved in it. And that's the reason why fish can survive in water with just that little oxygen over there. In steam systems, if we just take that water, produce steam like we do say in our domestic geysers, then what happens is this: when you heat water, some of this oxygen comes out because the saturation pressure of oxygen for dissolving in water decreases with temperature. The result is some of the oxygen comes out into the gas phase, and then if this reacts with the steel components, it will cause corrosion. And this is something we definitely don't want in a machine like a power plant or even a steam system of a submarine which is powered by a steam turbine, because we want that to last for 20, 30, 40 years. So we need to remove this. And what we do is, we just heat the water to a temperature of like 150 to 180 degrees Celsius and allow some of the oxygen to come out. So this reduces the concentration of oxygen in water, and then we get deaerated water, and that is then put through the boilers and the turbines. So what we have done is we put water into a tank, into which we also introduce steam, and this all mixes and collects inside the tank or in an adjacent vessel below this. So water is coming there, and this could be, say, water at about 130, 140 degrees or 120 degrees Celsius, compressed liquid. Here we put steam. This could be slightly superheated steam, and we adjust the flow rate of steam and water in such a way that what you get here is saturated liquid at 150, 180 degrees Celsius. The oxygen comes out here, and we have a small opening here through which water and some of the steam will continuously keep coming out. So that way what you are left here is deaerated water. So you have mixed compressed liquid with a superheated steam or dry saturated steam to produce a saturated liquid. The equations, everything will be identical to what I have just done, and the analysis of this can then proceed. In vapor power cycles, this is also called a deaerator, and it is combined with a temperature rise. Water came at 120 and it goes out at say 150. This is a deaerating feed water heater. And higher the temperatures that one employs of the steam, less is our ability to tolerate dissolved oxygen in the water. So as you go from 550 degrees Celsius to 600 to 700, we have to remove much more oxygen out of this water than what we have in, say, conventional power plants. So that's one of the engineering challenges, that if you want to increase the thermodynamic efficiency by going to higher temperatures, your oxygen dissolved in the water has to be brought down. There are a different set of things that one needs to put in place. Okay, there are two examples of mixing that I have given. The one thing that we will look at, okay, we have see what happens on the property diagrams. And I will draw the case of, say, the deaerator. That's the saturation dome. And what we have is compressed liquid coming from here, heated up to this point. And if nothing would have been done, this is constant pressure heating, so this line will go off there, and then it will go there, and then this will go there. And we are mixing this with, say, superheated steam at the same pressure or at a higher pressure over there. So we brought this in contact with this, mixed it up, and we got saturated liquid at this state. So what is the process that these followed? Well, we cannot in any way get back the original states without putting in extra work or heat or both. So these are completely, hugely irreversible processes. And this one comes down to here. And they come up to this state. If it was this state, it would have again come there, but you might, if you want to show it this way, that dotted lines coming there, that's okay. But even if you should just join it here and show it by a dotted line, because it's an irreversible process, that's also okay. So that's what we are doing here. In the case of the de-superheater, what we did, we had a state over there, a superheated state here, and we mixed water with it, which was at, say, this state, to produce a state which is at the same temperature, sorry, the lower temperature but the same pressure. So we came from 1 to 2 by mixing things. So we moved from here to here and there to there, but in this case we have moved from there and here to this place. One thing that we had listed there, what happens if you mix two saturated states? For example, we have dry saturated liquid in a vessel here. So this is a vessel in which there is only x equal to 0 at this condition. Say pressure P1 or temperature T1. Then you have another vessel at this state where x is equal to 1 at the same pressure, dry saturated vapor. And now we mix the two. It is adiabatic, there is no work transfer involved in this. We say just have a valve in between that which was opened up. It got mixed and the final state of the mixture was wet. So this could have come somewhere over here. Here, there, wherever it may be. So the question is this also reversible or irreversible? And one can argue that, look, if I have a vessel that you took all this mixture and you have put it in another vessel and allowed it to just stand there, we know that by gravity the liquid water will come down here, the vapor will stay up there, and if we can just take this thing out, we got our saturated liquid. Take this out, we got our saturated vapor, and so we got back our initial states. In some sense, this mixing of saturated states is a reversible process. Okay, it doesn't produce a new state in the sense that pressure and temperature are different, but we just produce a mixture where the proportion of saturated liquid and saturated vapor, they are different. So that was about the mixing of saturated states. And now we do the opposite of those things by looking at idea of separation. And separation basically means that we have a wet state and I want to separate out the saturated liquid and saturated vapor. An example where we really want to do this and do this most certainly is a nuclear power plant. So what happens in a nuclear power plant is that we have, say, we'll show it on the property diagram there. That's the dome. And in nuclear power plants, the steam produced by the nuclear reactor is at a state like this. It's a dry saturated state. This is the state at which we introduce it into the turbine. So this is the turbine. There is a shaft which is producing power. We got state 1 over there, and we allow the steam to expand in this, and we take it out at state 2. Now what happens here, that because it is dry saturated, the states in which the turbine will expand will all be along a line which is like this. And what it does is that as you keep going down, the dryness fraction keeps getting worse, from 0.99, 0.98, 9, 0.8, 0.7, 0.6, something like that. Which means that the amount of liquid flowing in a turbine is increasing, and this is largely dispersed at very small drops. And they can go and hit the blades. They don't follow the same expansion laws that vapors follow, so that design and engineering of this type of a machine becomes practically impossible. So what one does is that we say that, okay, I can make a machine and I will have exit dryness fraction more than, say, 0.9. So I can design a turbine and it's reliable up to this point. So at 0.9 we take it out. And then what we do is we separate it. So that this here, the liquid goes into this state, the vapor goes into this state, the mass fractions are less now. If it was 1 kg per second going in, now we have here, say, depending on the dryness fraction, it will be 0.9 kg per second here, 0.1 kg per second here. So this we have put into a device, and this is either separating by gravity or by inertia, that you just rotate this whole thing, the droplets will by centrifugal action go outwards and the vapor will stay inside. So in this we get the liquid coming out here, x equal to 0, and out here we get x equal to 1, dry saturated vapor, but not the full mass flow rate. We then take this and introduce it into yet another turbine and expand it further. And if you want, we can connect these two shafts together, and ultimately this is connected to a generator. So that device is called a separator or a moisture separator, either of these words. And how do we look at the thermodynamics of this? Well, this is a system that we can say that this is the system boundary, and this is of course an open system. So we apply the controlled volume approach. This is state 2 coming in, state 3 going out here, state 4 going out over there. We assume steady state, no change in kinetic and potential energy. It is a small device, no heat transfer. So Q dot Cv equal to 0. We didn't put any work in it. W dot Cv is equal to 0. And so the conservation of mass tells us that m dot 2 is equal to m dot 3 plus m dot 4. And conservation of energy tells us that m dot 2 H2 is equal to m dot 3 H3 plus m dot 4 H4. So we can then solve it out, and we can know what is the mass fraction coming out at this end. But all of this is happening at constant pressure. That means P2 equal to P3 equal to P4, and the same with temperature, T2 equal to T3 equal to T4. The only thing that we did, that here it was the specific enthalpy became HF, this is Hg, and this was H2, which is in between these two values. So that's the idea of a separator, and what we have done here is just put it through a passive device without putting any work or heat or anything else in it, and by inertia or by gravity we separated the liquid out from the vapor, and we get dry vapor coming out here, which we can then start using it again over there. So that's the idea of separation, and like we just saw, mixing, here we did not put any work or any heat, so if we just reverse all of them, we get back the state. So this becomes a reversible process, and on this picture we can say that this state went over there, this state went over there, and that's how we then have two streams from which you do two different things now. Now that takes us through all the flow processes, steady state flow processes that we have looked at. The cylinder piston arrangement is not a steady state, steady flow process, it's a closed system, so that's treated differently. Then we got a bunch of processes which are steady state. Now we look at some processes which are open systems, but they are not in steady state. So we look at filling and evacuation. So what filling means is that we have a tank, and into this, from a supply line, we are filling gas. There's a common example around us all the time that when a vehicle which has got which is running on CNG, it has got a CNG tank in the vehicle, and as the tank pressure keeps going down with use, at some point it goes back to the filling station. At the filling station, they connect a hose or pipe to it that is fed by gas from a high pressure reservoir. So we can say that this is a high pressure reservoir there, and when this valve is opened, this gas starts going into it and starts filling up this cylinder. That means during this process, we got flow going through this, and the mass of this and the pressure inside this keeps increasing. The P in the cylinder keeps increasing, mass in the cylinder keeps increasing. So it keeps doing this through an automatic system. It senses what is the pressure inside this, adds a little more, and as soon as the pressure of this, that is the safe working pressure of the cylinder, is reached, it stops and your vehicle is filled, then you have to go away. Now let's see what happens in this case. This is an example where we draw the system boundary, which is the space inside the cylinder, and say, well, there is one inlet taking place, but the state inside this keeps changing with time. So this is not a steady state situation at all, it is an unsteady situation. So we apply the first law, we have derived a very long equation, and we make various assumptions on that. We say that the state at which it is coming in, this is fixed and this is constant, this is state 1, and the state here keeps gradually changing. The mass conservation equation tells you that in a period of time, in delta t time, this m dot 1 into delta t is equal to the change in the mass of the system. And we can assume that there is no work being done here, work done is 0. It is an adiabatic process, this whole thing is insulated, Q dot Cv equal to 0. No change in kinetic energy or potential energy of either the system or the moving fluid, both are 0. And when we do that, what we will find is that this mass that went in, say a certain amount of mass, delta m in, its enthalpy H1, this is equal to the mass that got added over here. This will be, say this was evacuated initially, this will be delta mCv into UCV. Okay, that long equation that we had, if we solve it, remove things, this is what we will get, and it tells you H1 is equal to UCV. Okay, we are assuming that initially this was evacuated. And what does this tell us? If we are looking at CNG, which is methane, H1 we can say is CP0 T1, this is equal to CV0 TCV. It tells you that the temperature of the gas inside the control volume, TCV, this will be CP0 by CV0 multiplied by the temperature here. If this is ambient temperature, it means that this gas here will increase by 1.4 times the absolute value. So this becomes 1.4 into say 300, and that order becomes 420 Kelvin approximately there. So the temperature of the gas in the cylinder increases And if you actually go there and touch the cylinder after filling is done, you'll find that it is quite hot. You can't touch it. So it has reached a high temperature, but the pressure is equal to the maximum possible pressure to which it can be filled, which was 200 bar. So you got gas at 200 bar, but temperature which is much higher. And the safety of the cylinder requires that pressure should not be exceeded. Which means that if you fill it up here and this is at a high temperature, as you go away after some time, even if you don't use the gas too much, the pressure inside will drop as the temperature reaches the ambient temperature. So instead of say about 80, 90, 100 degrees Celsius, this will then come down and the pressure will be less. But you cannot initially fill it up to more than this, hoping that after it cools down it will come to 200 bar. That is not permitted because the mechanical design of the cylinder does not permit us that. So that's what happens in a filling process there. And this is one set of problems that we tackle. The trouble is that since the state of the substance inside this changes with time, one have to be very careful that when we apply this equation, it is only for short periods of time. And the mass that is put in is also of a very small limited amount. Otherwise, technically, the type of integration that we did to get delta MCV, that cannot be done. One then has to say that, okay, I will take a small time, see what happened, then I will take that as the starting condition and see what happens after a little more filling. Then I'll take that as my starting condition and see what happens after filling. And that's how the calculation will proceed. It is a little more complicated, and so we do not do it in this beginning course. But it's important to know that this is what filling does, and there are many other cases where such things happen. We can look at the fact that if this was saturated liquid and this was evaporated, what will happen? And that's the example when your LPG cylinder goes for filling. It is initially evacuated and then you are pumping liquefied butane into it. And we can say that, well, I am putting in some liquefied butane. Am I actually getting liquid butane inside the cylinder at all times? I'll leave that question to you to think of. The opposite of this is evacuation or emptying. And what we do here is we are the opposite of what we have just looked at. We have a reservoir, say an air reservoir, from which we are taking in air. Almost every manufacturing unit, every factory will have some requirement of compressed air. So from a compressor, we keep filling into it and keep drawing it. So the analysis of this, if we want to do, we want to know, well, what is the relation between mass flow rate and the pressure in the cylinder. We'll do the same analysis like what we just done a few minutes back. That this is our system boundary. We say that this is an open system, control volume approach, but this is not steady. So we apply the same equations and say that, look, there was certain mass here, it went out, its internal energy became its enthalpy over here because there was flow work coming in. So this enthalpy and the internal energy that was here, these will be equal, and you will start seeing decrease in temperature as you draw out the gas. One of the problems in one of the assignments that I put is that instead of just having gas inside this or air inside this, I've given the example of the domestic LPG cylinder. And what do we actually do in the domestic LPG cylinder is that we are drawing air from the top, and of course there is a regulator sitting on top of it over there. So you are drawing off only the saturated vapor. And as we keep drawing out, this evaporates. The temperature inside this, you can do the calculation and see that temperature keeps decreasing. But fortunately, in domestic cooking, we do it so slowly that we don't see this temperature rise. Whatever temperature fell, the ambient would supply energy and it will come back to the same temperature. So we are drawing off saturated vapor, dry saturated vapor, even though in the cylinder as a whole, we had a wet state. There is liquid there, there is vapor over there. And as we keep drawing out, this level keeps going down. But if the temperature were constant, we always had the wet state at the same condition. The dryness fraction of the system kept going down. So inside supply pressure remains constant as long as there is liquid inside the cylinder. And that's the nice thing about the cylinder, and the pressure regulator is able to do its job quite nicely. Once the liquid is gone, you have dry saturated vapor, and then when you keep drawing out, there is no more liquid to evaporate, then the pressure on the cylinder begins to go down. And that's what I just mentioned, the pressure regulator then cannot do its job. So the pressure regulator is designed for the fact that butane will come out at a certain pressure, it will throttle it and produce a pressure which your LPG stove actually wants. Analysis of this proceeds exactly the same way as before, so I will not repeat it, but you can write the full equation. Again, make the similar assumptions that heat transfer is 0, work transfer is 0, kinetic potential energy changes are 0, and simplify the equation and solve it. The only difficult thing that happens in this type of problem is that if you want to figure out and say, what is the pressure after I drew out so many grams of this substance, then in the final case, you are left with something like two properties which are specific internal energy and specific volume. And knowing these two properties, the state is completely defined. But we do not have any nice property tables which tells you that if you know U and you know V, this is the way to calculate P, T, H and all the other properties. This is complicated, quite troublesome, and you have to in some cases do iteration, and even online programs which are there, very few, rarely if any, give you the option that you specify U and V and it will tell you what the state is. It's not all that straightforward a calculation, but even if you get to the point where U and V are correctly identified, the state is fully known, you can say, well, at least I reach 99% of the problem has been solved, 1% is to use the property tables and get these values. So you can even get and quit it at this point. So that is one of the issues of filling and emptying. So what we have done now is we have looked at all types of processes that are possible. We looked at a closed system, cylinder piston arrangement as the simplest thing, but we also saw that its counterparts are screw compressors, scroll compressors. They all do basically the same thing. They trap the working fluid and change its volume and impart energy to it. Then we looked at open systems in steady state and saw that these are the common engineering things from which we have to design everything else. Then we saw open systems in non-steady state. And during this discussion we said that depending on the type of machine we are looking at, this machine has certain characteristics. For example, we said that if it is work in or work out type of a machine, then Q dot is not possible. We cannot make a turbine where you can cool it or heat it at the same time get the working substance to expand. Same thing with the compressor, that if we say make me a compressor where I will compress it and at the same time heat it also, such a machine cannot be made. So we are now seeing certain restrictions on what happens. When we looked at tubes and heat exchangers, we saw that what is possible in the real world is constant pressure heat transfer. You say you make me a device which is isothermal heat transfer, the only thing we can do is to have phase change. But if we don't have phase change, which is not possible with an ideal gas, making an isothermal heat transfer device practically is not possible. Theoretically, yes, it is there. Practically, the engineering just doesn't work out and you don't see those things in the market. Nobody makes it. So we have to make some compromise and say, look, if I have a heat transfer process, I will have to assume that it is constant pressure. If I have to lose some of the reversibility in the process, so be it. That's my compromise. So these are the type of things we looked at. And now let's ask the question that given the same thing happens in the cylinder piston arrangement. If we say that in the cylinder piston arrangement, if I have to have isentropic expansion, we said, okay, fine. Insulated, no friction in it, it will expand, you get isentropic expansion. That's fine. But if we say that I want isothermal expansion or isothermal heat compression, we have a problem. Isothermal expansion would mean that when the gas expands, we know its temperature will come down. If I have to make it isothermal, that means I have to supply heat. So the compression process means the piston has to move and heat has to be added. Two things have to be done simultaneously. In isothermal compression, you have to do the opposite. So there are big problems that we cannot design isothermal compression or isothermal expansion in a cylinder piston arrangement. The next best thing that we can see is what we see in practical engines. I can make the closest we can get isothermal is isochoric heat transfer, which is your petrol engine, or isobaric heat transfer, which is your diesel engine. But we are not able to produce isothermal heat transfer. This has implication in both cases on the Carnot cycle. And how do we go from Carnot cycle to various practical cycles? The other thing we looked at, we cannot make a work producing or a work consuming device which has a mixture. It has to be either fully liquid or it has to be fully vapor or an ideal gas. We cannot pump in a wet state. We cannot expand wet steam very much in a turbine. Up to 0.9 quality we can do it, 0.6 quality, 0.3 quality is not possible. So thermodynamics tells us you can do it, practical engineering tells us not possible, don't worry about it. Try something else. So what we will do is, before we look at the practical cycles, we will now revisit the Carnot cycle and say, well, what is it that is possible in closest to the Carnot cycle and what is not possible in the Carnot cycle. And that will tell us what becomes a practical cycle. So that's what we are going to look at next. So what we are saying is that we will look at practical realization of a Carnot cycle. And we have 4 possible combinations. The working substance, as we have now learned from this course, is that I can either treat the working substance as an ideal gas or we treat it as a vapor. So there are 2 distinct categories of working substance. We also learned that we can have a closed system or a flow system, which is something flowing through a circuit. And it tells us that I can make an ideal gas in a closed system, which is a cylinder piston arrangement, or I can make vapor with a closed system, again a cylinder piston arrangement, or type of scroll arrangement. So that's 2 types of cycles that one can make. We can also make an ideal gas and say that I'll put it through a flow system and make a Carnot cycle. Or I can take vapor and put it through a flow system and make a Carnot cycle. So it tells me that we can have 4 possible ways in which we can think of a Carnot cycle here. What happens in the first module, in the second module we had learned that to make a Carnot cycle, on the TS diagram what we said was there has to be 2 isothermal processes, 2 isentropic, and 2 isothermal. And we started with the argument that I want everything to be reversible, and if everything is reversible in a cycle, that is the best cycle that we can make, and that is what we said in the Carnot cycle. And from there we argued out why we have to have these 2. So that was the basis on which we conceived the Carnot cycle as these 4 processes as the best cycle possible. So now there are 2 things possible. Either this cycle could go in this way, that way. That means it starts state 1, state 2, state 3 and state 4. And we see here that if say take process 3 to 4, then delta Q is equal to TdS, and we integrate this from state 3 to 4. This will tell us that this is T3 or T4 into S4 minus S3. On this picture, this expression is this area. And in this case, the cycle is going like this. So this S4 is less than S3. So you have Q dot or QCV, whichever way you want to see, Q34. This is heat rejection by the system. Then, if you do the same thing for 1 to 2 process, we get the similar type of a thing, which will then be T2 S2 minus S1. And so this entire area, this is heat input to the cycle. And what is left to us is that the difference of these 2, which is the cyclic integral of heat, this has to be equal to the cyclic integral of work. This is the work output of the cycle, which would be the area inside this rectangle. So graphically, this is how we are able to conceive it. This way, it is a heat engine. If the cycle goes in the opposite direction, this is a refrigerator. And now we will see how can I put this cycle in the real property diagram for an ideal gas and a vapor, and see what practical issues will crop up. Okay, so let's go back to the, first let's look at the ideal gas. How do I realize these processes, and we'll put that up on the PV diagram. I have shown a heat engine here. The opposite of that will be the refrigerator. So to bring it on this diagram, let's first look at something we have learned now in the properties of a pure substance, that on a PV diagram, a line like this is N equal to K, which is the isentropic process. And a line like that will be N equal to 1, which is the isothermal process. This is S constant, that is T constant. So we can put these two lines. This is isothermal, and the other line, this is isentropic. What it tells us that we can show this cycle, I need to make two isentropics and I need to make two isothermal lines. And that's what I've drawn in this thing. So we will say that the isentropic lines are here. This is one isentropic line and this is the other one. This is S2 equal to S3, this is S1 is equal to S4. Now we draw the isotherms. So this is one isotherm and this is the second isotherm. And now we complete the mapping of the states into this. This is state 1. This point where these two intersect, that is state 2. This is state 3. This is state 4. So now let's see what is it that we get. And what we are looking at is, let's say I have a cylinder piston arrangement into which we move this piston up and down, heat it, cool it, and get work out of it. So volume tells you where the position of the piston is in that sense. So what it tells you is that this is the maximum volume in the cylinder piston arrangement. So state 3 will be somewhere there. We compress it and come to some point to state 4. And this is an isothermal process. So during the isothermal process, which is your 3 to 4, we have to have the piston moving and your heat rejection. So we have to have two things in the practical world, that the piston is moving and we are very quickly taking out heat from there. That's one thing. 4 to 1, the piston further moves up here, comes to state 1. This is an isentropic process. That means there is no heating, no cooling, it's adiabatic and reversible. So ideally, if there was no friction, it could go from here to here. So this is isentropic compression. That's fine with us. So first part was your isothermal cooling. while the piston is moving, followed by isentropic compression, which practically, if we do the best we can possible, we can argue, I can get very close to it. That's something we can get close to. This is a big problem. You cannot have that much heat transfer taking place from a cylinder in a very short period of time. That brings us to state 4. So we started here, we can call this as state 3. It came to 4 as an isothermal process. Now 4, it comes to 1. Okay, so that was the isentropic compression. From state 1, we are getting this line, which is an isothermal, which is 1 to 2. And during this process, the piston moved from there and came out, say somewhere here. This is state 2. And what did it do? It of course expanded, but 1 to 2 here was Q in. So you are expanding the piston at the same time trying to heat it up. Same problem as 3 to 4, where while compressing it, you are trying to cool it. That little piston that we have, say in a motorcycle or a car, it's just not possible to do that type of heating or cooling in a very short time. But isentropic compression is followed by isothermal heating. So this is a big question mark, cannot do. Isothermal heating is the next big question mark, we cannot do it. And then 2 to 3, this is isentropic expansion, and we can say, well, not isentropic, but I won't take out heat from it, I won't cool it, but yes, I can get very close to it, not N equal to K, but slightly less than K. So in realizing the Carnot cycle in a gas, in a cylinder piston arrangement, there are two things which are not there in the world of engineering, which is that you do a huge amount of cooling while the piston is moving, or a huge amount of heating when the piston is expanding. This is not possible. So we have a problem in realizing the Carnot cycle with gas, or even trying to get close to it in the real world. This is a problem we have here. These processes and states will remain the same if instead of a cylinder piston arrangement, this was a closed system, we wanted to realize the Carnot cycle in an open system. And what we would do then is, if we have to compress it, we will put it through a centrifugal compressor, and in this case we have a centrifugal compressor which is being heated up. Again, that's a device we saw in our earlier discussion. Compressors will treat that as adiabatic. They can be made, but to have a large amount of heat transfer during the compression process, we can't make it. Then we have an isentropic compression. That is possible. The ideal compressor would be that we just compress it. So most compressors you see, whether it's in an aircraft engine or in a gas turbine elsewhere, this is possible. We can get very close to it. So this is not a big problem. 1 to 2 is an expansion, so we have to use a turbine. And turbine in this case is isothermal turbine. That means when it is expanding, we are going to heat it also. This is not possible. You can't make a turbine and straight heat it up. The practical turbine, I said, what we can make is an isentropic turbine. That's the best we can do. This is again not possible. The last part is an isentropic turbine. We can do that and get close to it. So even in an open system, what we are seeing is we need 2 compressors and 2 turbines, 2 adiabatic, 2 with heat transfer. The 2 heat transfer ones are not possible. So again, the Carnot cycle as an ideal gas cycle, we cannot come close to it. This is the problem with the practical realization of the gas-based Carnot cycle. Okay, so that is what happens to the Carnot cycle with the gas. Now let's look at what happens to the Carnot cycle in the flow system. So here we have the TS diagram, and what we have here is the saturation dome we have to work with. We are dealing with a vapor, so we have to show this. And now what happens? Let's say any rectangle that I can put on this is a Carnot cycle. I said, okay, so we put a rectangle over there, that's the Carnot cycle. We are far away from the dome, so this is an ideal gas, And we just argued that whether it was flow system or a closed system, we cannot make this, or we cannot come close to it also. Now let's see what happens here. Somebody says, well, I'll make a Carnot cycle like that. And what do we see happening? This is the turbine process. Superheated steam going in, superheated state coming out. It doesn't matter what the working substance was. If it's steam, it's okay. If it's some organic chemical, that's also okay. The next problem happens here. What we are seeing here is that this is a constant pressure line here, and this is a constant pressure line here, and as you go up, pressure increases. So this process from here to here, cooling is taking place. That means you are rejecting heat. So this is cooling, plus at the same time, pressure is increasing. You cannot increase pressure without doing work. So that becomes a complicated process. We don't try to do it. Next part is here. From here to here, we have condensation taking place. That's not a problem. We can make a heat exchanger to do this. The next process is this vertical line. This is your work input process. And here we have a wet state there, and wet state all the way through. And we just said that if you are going to make a compressor or a pump or anything, it has to either handle only a liquid or it has to handle only a vapor. This is handling completely a wet mixture. In the real world, we cannot make such a thing. So this is not possible. This is isobaric evaporation. From here to here, no problem, we can make it. But from here to here, when we are adding heat, this is the pressure here, this is the isobar here, this direction, the pressure decreases, which means that you have to make a device, a heat exchanger, where there is heat transfer taking place to the substance, at the same time the pressure is decreasing. Again, not possible. So we cannot get these two things, and we cannot get this thing. So that's the reason this cycle will become impractical. So let's see now what are the other options we have and what are the closest that we can get. First, let's try to avoid heat transfer processes where there is a pressure change. So I will not make a device in which I will have heat transfer with pressure change. I will make a device where heat transfer takes place at constant pressure, constant temperature. That fortunately for us works out, and we can say that I will have this as my heat input device. Phase change is taking place, x equal to 0 becomes x equal to 1. Constant pressure heat transfer, entirely doable. Fortunately, because it's a saturated state, it is also constant temperature heat transfer. So we got two advantages in the same shot, that we got isothermal heat transfer, something that the Carnot cycle wants. We got it. The next thing, we have to have an isentropic process from this point. So this process will come down there. Here we have a little problem, that as you come down, the dryness fraction keeps getting less. So we are getting into a wet zone. But if the dryness fraction is like 0.9, 0.95, it is not too much of a problem. Machines have still been made, they are reasonably reliable. So it's, unless it goes down to very low dryness fractions, then this is not possible. Then we want to now have heat rejection. So we get this process, and we say this is the temperature at which we are rejecting heat. Condensation is taking place, temperature is constant, pressure is constant. So what we got here is isothermal cooling or heat rejection. This was isothermal heating. Possible, entirely possible to do it. And then we say, now to complete my Carnot, the last process to put is this one. And here we run into a problem. That well, what you have here is a wet state and you are trying to compress it to make it a liquid. I cannot make this machine. So this cycle came very close, that we almost got this. These two we are able to get, this we cannot get. And so this cycle is very close to being realized, but not realizable. So what do we do next then? What we have is a modification of this Carnot cycle. And we say that, look, I want to make it practical. So instead of condensing it here, we will take it all the way there and condense it over here. So this to this is condensation. Now we have liquid, we can make a pump and compress it. And at this state, we can then begin the heat input process and it will go from here to there. So now 1, 2, 3 is our heat transfer process. It is happening at constant pressure, so possible. This expansion is happening here, and we are still saying that, okay, if I can get down to 0.9, I am okay. Otherwise, I will have to do something else here also. And we will see in a minute what else we can do this side. From here to here, we bring it down all the way. So this is, say, state 4, say 1, 2, 3, this is state 4, this was state 5, this is state 6. 6 to 1, pump, realizable. 1, 2, 3 heat transfer process. 2 to 3 is isothermal heat transfer. 1 to 2 is not isothermal heat transfer. So which means that I have sacrificed something over here. 4 to 5 is isothermal heat transfer, that's fine. 3 to 4 isentropic expansion, except for the dryness fraction problem in the that is there. This is okay. And this becomes the first practical cycle that one could make, and this is called the Rankine cycle. And in some sense, this is what the first steam engine was all about. You had a boiler into which we pumped water at ambient conditions. So that was like 1. The boiler heated it to produce steam, which was somewhere there. This steam was taken out of the boiler and put in the cylinder piston arrangement and expanded. So that expansion wasn't exactly like this, but very close to this. And then after expansion, that was an open system, that steam was thrown into the atmosphere. And then we keep getting fresh water, put it in there and do this process, expand it, throw it out. So 4, 5, 6, the heat rejection process was not there in the original steam engine or any steam engine that came afterwards, but this formed the basis of trying to make the flow type of a power cycle, which is the standard thing now in all types of power generating systems. So before we go there, let's look at this process 1, 2, 3 and see what does it tell us about the thermodynamics of it in the context of a qualitative way of looking at how good is my Rankine cycle compared to the Carnot cycle. Okay, the Carnot cycle, ideally, if we had made it up to this point, we would say, well, make a cycle which is like this. Then you would have got the Carnot efficiency, or this cycle would be the same Carnot efficiency, but what we have done now, instead of this cycle, which was the Carnot cycle, we have gone this. Our efficiency has come down, and let's see how and why and by how much. So for that, we will look at the process separately. Okay, so this is the process that I have drawn here. This is a constant pressure line there, and constant pressure line there, and the constant pressure line that goes over there. And now we know that these are all compressed liquid states, and this is a saturated liquid state. So we ask the question, what is all the heat which was added from 1 to 2, whether it's a closed system or open system, doesn't matter. Let's just say that, say this Q12, or flow system would be Q dot. We added heat at some temperature, then little more at this temperature, then little more at this temperature, little more at this temperature. So if I have to make it on a TS diagram, and we put all these states together, then we do what we did for this part, integral TdS as the heat added in that process. But now what is happening is, we have a process where entropy is increasing and temperature is also increasing. So if we know explicitly T as a function of S, we can integrate this. The next best option is what we do now with computers, is to do a numerical integration and say, well, look, I will say that we'll divide it into very small steps where there are small changes of entropy. And this is the heat added in this part of the process. So this much heat was added, and I say, well, at what temperature did we add this heat? We'll say that we'll take the midpoint of this and say that this is the temperature at which this much heat was added. This we will do now with the next one also. So this one, then with this one. So then we will say, okay, now what happened in this part? Well, this much heat got added, and the average temperature at which this heat got added was this much. So like that we can integrate it and then compute from here that this much heat was added at this temperature, this much at this temperature, this much at this temperature. So we can get some sort of an average temperature at which we added this heat. And this temperature was constant there, say we call it T2. And then we say, well, what the total heat that we added in this process, which is this much. If I have to say what is the average temperature at which we added this heat, then I can approximate this area by a rectangle which is like this, which has the same area as the area under that curve. So this area and that area are equal, that means the same amount of heat was added. But now what we have learned is that this is the average temperature at which heat transfer takes place in the process 1 here and here. And that is to be expected because now we are adding heat to a lower temperature. So T bar, this T average temperature, is now less than T2. And so the Carnot cycle efficiency, which was entirely dependent earlier on T2 and the state here, which was T4, there the efficiency was 1 minus T4 upon T2. Now, yeah, 1 minus T4 upon T2. The T2 has now come down and it has become less, and so the efficiency of this cycle is going to be less than the Carnot cycle efficiency. So in that sense, Rankine cycle efficiency is less than Carnot cycle efficiency. We made that sacrifice, but in the process, we have made a cycle which is very close to practically making it. On top of that, there will be irreversibilities of friction, sun expansion, heat loss, all of that. So the efficiency will be further less than the ideal Rankine cycle. The real cycles will be less. But we moved out from seeing that the Carnot cycle was practically impossible to make, but we said at least in one case, we are able to make a modification here and realize something close to a Carnot cycle. In the case of gas cycles, we would replace isothermal heat transfer processes by either isoporic or isobaric heat transfer processes, and we'll see how we do that a little later. But this is what we did. The next thing what one does is, how can I reduce this problem? That the dryness fraction here is very low. I want to have turbine which is very close to over there. And the answer for that is that I'll show it on this diagram. I want to take 0.4 from here to here, very close to 1. That means this is a state at which the steam's expansion in the turbine comes to an end. So the turbine processes have to lie on a vertical line which goes up here. Okay, so what it tells us that I have one restriction of that the states at which the steam comes into the turbine has to lie on this line, and I have a second restriction that the state at which the heating will end will be on this isobar. So isobar, which was here 1, 2, 3, we continue that isobar and say, well, look, this is isobar at which heat transfer takes place. The intersection of these two is the state at which the steam should leave the boiler and enter the turbine. So that's what we did. If you do that, this line comes up over here. The average temperature at which now heat is added has increased a little bit because we added this heat at a higher temperature. So cycle efficiency has gone up, and we got this problem also solved, that dryness fraction of steam in the exhaust of the turbine has improved, and we said, look, this is a nice cycle, it meets all our practical requirements, and the first power plants were made with this cycle. And that's how the idea of this heating which is superheating, this has come about. So almost all cycles, whether it is nuclear or whether it is ocean thermal or solar thermal, all of them will be something or some variant of this basic Rankine cycle. So this is Rankine cycle with superheat. Okay, so this becomes a practicable cycle and all engineering happens with this. And the reason for bringing this up is very simple. If I want to increase the efficiency of the cycle, I have an option of reducing this temperature or increasing the average temperature at which heat input takes place. This is isothermal heat transfer. So this is dependent by the condenser, which is directly related to your ambient. We cannot play too much with the ambient. We are dumping too much heat into the surrounding, the water body, ocean or a river or a canal, that has to take away the heat, or the atmosphere has to take the heat. Idea is, how can I increase the temperature at which we added heat, the average temperature at which we added heat. So everything we want to do is to take this point as high as possible. And this very simple fact becomes the basis of doing all R&D related to not just steam power plants, but also gas turbines, aviation turbines, everything. So what we see happening in the real world as greater and greater efficiencies happened because of this very fundamental motivation that comes from very simple thermodynamics that we are now learning. That's the far-reaching implication of what we do. So this temperature kept going up, and that's what happened historically. 1920, the first power plants were made with very low pressures. The first steam engine was something like 3 bar, 4 bar pressure, very low. Then this temperature started increasing, they kept going up. And the way we could do it was happening because of two things. When they would increase this pressure, the devices would break, fail, explode. And so that needed new materials and better manufacturing process. Remember, the beginning of the industrial revolution started with casting, and riveting came very quickly. That's how pressure vessels were being made. Later on we started getting steels, then we started getting welding, and as those things started happening, then came forging, hot rolling, and with each one of them came alloys. We got alloy steels, and with each one of those things, this temperature kept going up. And that's what's happening now also, that we are trying to increase the current limit of say like 565 degrees Celsius. There's effort to increase this to 710 degrees Celsius. This will take another 5, 6, 8 years to happen, but the big challenge here is the material and how do we make it. The thermodynamics tells us that, look, this is what you need to do, which material to use, how do I manufacture it, what is its cost. This is where a lot of research also is going to happen. But all of that research is coming from this motivation, which is coming from this motivation. Okay, so that was an important thing, that how do we quantify the average temperature at which heat transfer takes place in a cycle. So that was the Carnot cycle coming in there. We'll take a few minutes to look at the gas cycle, and then we'll have questions coming in. What happens in the gas cycle is we modified that diagram and said, look, isothermal heat transfer is not possible. So what we do, and we have to do it on a PV diagram. We saw that PV diagram that was coming up. It was like this, then like this, then like this, and then like that. Not practical. So we said isentropic process I can very closely get, but then don't bother too much about anything else. So what we did is we took this isentropic process and took it all the way here. And then we said I can do two things. I can do constant volume heat addition, or I can do constant pressure heat addition. If we do constant volume heat addition, we then have this expansion isentropic, and then I said constant volume heat rejection. And this becomes the Otto cycle, or this is the thick thermodynamic cycle for the petrol engine, or what we call as the gas engine, the CNG engine or the LPG engines. Or when we went into this route, then we got the diesel cycle. Okay, clearly both are quite different from the Carnot cycle that we would have liked to have, but this is what is practically possible. And what we have done here is that in this cycle, we put in a mixture of air plus fuel, ignited it suddenly, its pressure went up, that got approximated as a heat transfer process. And here we open the exhaust valve and let everything come out and expand to ambient temperature, and we got that as the cooling, equivalent of a cooling process. In the diesel engine, during this process, we injected fuel, increased the temperature, and then stopped the fuel injection at that point when the piston had moved a little bit and allowed it to expand, so-called isentropic process. And then we got this thing. So both cycles became practical, but both cycles have an efficiency less than the Carnot efficiency, but both are practical. So we'll stop by making one more thing, that what we have drawn here is something what we will call as an air standard cycle, and versus a ideal gas cycle. Oh, sorry, the real cycle. And I will list the differences between these two, because air standard cycle, the one whose performance we can analyze, we know all the equations and processes for that. Real cycle is complicated and subject of higher courses and practical engineering, but this is the beginning point by which we start getting qualitative ideas about what happens here. So what happens here is that first, the working substance here is air, which is assumed to be an ideal gas. Here the working substance is air plus a mixture of the combustion gases, and that would actually behave like a real gas. The second thing is the heat addition that we show on these diagrams. In an air standard cycle, it is a closed system where externally it is heated and cooled. In the real cycle, the heating process is replaced by the burning of fuel, and burning fuel in the working substance itself. So the working substance doesn't even remain in the same air. And heat rejection, so heating is like that, and heat rejection is also closed. Heat rejection is replaced by an exhaust and fresh intake. So in this cycle, ideally we would say that the same mass of air which is undergoing these processes, in the real cycle, we say that after this process is over, we throw everything out and get fresh air in, and we come to this state. So that's the approximation we do. So there are three major differences between the air standard cycle and the real cycle. The reason we make these differences is that air standard cycle can be analyzed from everything we have learned so far. And from there, we can calculate at least efficiency, heat transfer, work transfer for each process that can come. We know the parameters of the cycle, maximum pressures, maximum temperatures, all of that can be calculated. In the real cycle, we'll have to go to much more sophisticated programs. They are now there, all designers of engines and all, they will do this part, but that's how they'll actually make the machine. But for beginning purpose, we take the air standard cycle assumptions and analyze the cycles. Okay, there are some questions. Okay, the second question, there's a question here, what types of modification is done for Carnot cycle? and that is easy to answer because I just showed that for gas cycles, this is the Carnot cycle. And I will summarize that again, that we replaced the isothermal heating and cooling. We replaced the isothermal part by either isobaric or by an isochoric process, constant pressure heat transfer or constant volume heat transfer. That's what we have done. In the vapor cycles, the modification that we did is that instead of getting wet states here, we condensed it all the way to a saturated liquid and then compressed it. And then we started adding heat. So the heat transfer is not isothermal heat transfer. So what here also we did the same thing. We replaced isothermal heat transfer, isothermal heating. Isothermal heating got replaced by isobaric heating. This got replaced, but isothermal cooling is still there because we are condensing it at constant temperature. So in vapor cycles, we replaced isothermal heating by isobaric heating, and in ideal gas cycles, we replaced isothermal heating and cooling by isobaric heating or isochoric cooling. So we replaced both processes here by something else. In the vapor cycle, we only replaced the isothermal heat transfer process by isobaric heat transfer process. That's the difference we have. Okay? So that's the question. Then what are the effects of friction in a nozzle and a diffuser? So that's the question now. Effects of friction in nozzle or diffuser. Okay, so here is what happens. Say we have a nozzle and the fluid is flowing like that. This is our control volume. Now what friction does is dissipates energy which gets converted into internal energy, raises the temperature of the fluid, and the velocity that we get is less than what we would have got. So in the nozzle, say this was the inlet state 1, the isentropic nozzle where there was no friction would have come here 2 and say 2s isentropic. But what is happening is this is the constant isobar there and this is the isobar. So this is the line of P1, this is the line which tells you where is P2. So this was the isentropic nozzle. The real nozzle, because of internal irreversibilities, its entropy has to increase. But if we expand it from the same inlet pressure to the same outlet pressure with increasing entropy, that means the state has to lie somewhere there. Entropy has increased, pressure is still the constant, and now the real nozzle, because of friction, does this thing. Okay, the diffuser does the opposite. So it has increased the area and increased the pressure from here to here. So the initial state was there, it went to that state. So this is TS. These are the two isobars, P1, P2. And now if there is friction inside this, what it will do is it go there somewhere and the temperature will also increase. So that's what the diffuser will do. So that's what the difference between the nozzle and the diffuser. And the way we characterize this is that isentropic efficiency, as we defined earlier, if you recall the third module, this was defined in the case of a nozzle as velocity change in the real case divided by velocity change in the isentropic case. In the diffuser, the pressure recovery will be the opposite of that. So that is for nozzles and diffusers. So tomorrow we will look up some design problems of how we make a system, and we'll solve some problems in tomorrow's class. Okay, thank you.